Okay, let's dive into this. Look, when it comes to linked lists, a lot of people fall into the trap of just trying to memorize chunks of code for every single problem. But today, we're not going to do that. We're going to do something way more powerful. We're going to master the underlying navigation patterns that turn these tricky problems into, well, simple walkthroughs. So first, just a quick refresher, right? A linked list is basically a chain of nodes. Each node has some data, and this is the important part, a pointer to the very next node in the line. Think of it like a one-way street. You can only move forward one step at a time until you hit that final null, which is just a dead end. And that one-way nature, that's the whole challenge, isn't it? If you can only move forward one step at a time, and you can't just jump to an index like you can in an array, how in the world do you navigate one of these things effectively to solve complex problems? Well, it all starts with the absolute bedrock of linked list techniques, the basic walkthrough. This is the foundation that pretty much everything else is built on. And the idea couldn't be simpler. You're going to love this. You just create a temporary pointer, let's call it current, start it at the head, the very beginning of the list, and you just walk. You follow the next pointers node by node until current eventually hits that null at the end. This simple little loop is the secret key to a huge number of common operations. And check this out. This is where you really see the power of recognizing patterns. On the left, we're counting how many times a value shows up. On the right, we're removing every kth node. Now, they sound like totally different problems, right? But look closer. They're both just that basic walkthrough. The only difference is the little piece of logic you stick inside the loop, either an if statement to check a value or a little counter to track your position. It's the same pattern, just solving different problems. But what happens when that simple walk just isn't enough? Let's look at a problem that forces a real paradigm shift in how we think about moving through these lists. All right, here's a classic. You've probably heard it in an interview. How do you find the middle node of a linked list? Now, here's the real kicker. You have to do it in a single pass. You can't go through it once to count everything and then a second time to find the middle. Just one shot. Now, the obvious way to do this, the naive approach, is exactly what we just ruled out. You walk the whole list once to get the total count, let's say it's n, then you go all the way back to the beginning and walk it again, stopping after n divided by 2 steps. I mean, it works, sure, but it's super inefficient. We can do so much better. And the solution is this beautiful, elegant idea called the hare and tortoise algorithm. Get this. Instead of one pointer, we're going to use 2. We'll have a slow pointer, our tortoise, that moves just one step at a time. And we'll have a fast pointer, our hare, that leaps 2 steps at a time. Okay, let's watch it in action. So, at the starting line, both the slow and fast pointers are right at the head of the list. And they're off. In the first step, the slow pointer plods ahead 1 node, while the fast pointer jumps ahead 2. And this process just keeps repeating. Every single time the slow pointer takes 1 step, the fast pointer takes 2. You can already see the gap between them is growing. The fast pointer is literally racing ahead. And here is the magic. By the time our fast-moving hare reaches the very end of the list, guess where our slow, steady tortoise is? Bam! Pointing right at the middle node, because it's been moving at exactly half the speed the entire time. And what's so cool is that this works perfectly for lists with both odd and even numbers of nodes. It's just a brilliant, efficient, one-pass solution. Now, let's see how we can build on this, because this powerful 2-pointer technique is not just a one-trick pony. We can adapt this exact same hare and tortoise pattern to solve a completely different and maybe even trickier problem. So the new problem is this. How can you tell if a linked list has a cycle in it? As you see here, a normal linear list just ends in null. But a circular list has a node somewhere that points back to a previous node, creating an infinite loop. So how do you detect that loop without getting your program trapped in it forever? Well, you guessed it. You use the exact same 2-pointer approach. And the logic is summed up perfectly here. If the list is just a straight line, the fast pointer is simply going to run off the end and hit null. But if there's a loop, it's like a racetrack. The fast pointer will eventually come all the way around from behind and actually lap the slow pointer. And this really illustrates the only 2 outcomes possible. If that fast pointer, or the node right after it, ever becomes null, we know for sure the list is linear. Game over, no cycle. But if the fast and slow pointers ever point to the exact same node, that is definitive proof that you are in a cycle. There's no other way they could have met unless the fast one laps the slow one.
So let's just zoom out for a second and recap what we've really done here. We haven't just solved a couple of isolated problems. We've added two powerful, flexible patterns to your linked list toolkit.
Ultimately, it all boils down to recognizing which tool you need for the job. For simple stuff like searching, counting, or just basic modifications, that single pointer traversal is your go-to. But for these trickier problems involving halves, cycles, or relative distances between nodes, the two-pointer hare and tortoise technique is your secret weapon. The point is, it's not about memorizing code. It's about recognizing the shape of the problem. By really understanding these core patterns, the simple walk and the two-pointer race, you've pretty much unlocked the ability to solve a whole class of linked list problems. So the question I want to leave you with is this. Now that you've mastered traversal, what other complex list manipulations can these pointer patterns help you solve?